Welcome back to DemystifySci. I'm Shiloh.
I'm Anastasia.
And this is the point where I usually would give a catchphrase telling you what this podcast is all about, but I've been thinking a lot about that lately, and I think what we're really trying to do here is reinvigorate the spirit of something that was lost in the middle of the 20th century in the scientific landscape. And that is the spirit of free and open conversation between theorists, where folks can play with ideas without being attached to the eventual outcome. We recognize science as this ever-evolving landscape of theories, and something very bizarre happened where it got tied up into careers and peer review and publishing and consensus narratives. And we don't see that when we look into the history books of the Royal Society. We see these really open letters between very often dispassionately oriented theorists who are trying to just compare notes on how they think the natural world works. And I really think that the science podcast space, if we can call ourselves in that, are we science podcast? This space is really unique in this moment because it allows theorists to come together and expound on ideas that might not be fully fleshed out yet. They might not be ready for prime time, but we can play with ideas.
Today's conversation is a perfect example of this mission because we have an applied physicist with us who has been trying to resolve a bunch of really disparate questions about the natural world. With us, we have Dr. Anne Hofmeister from Washington University in St. Louis, and she has an unconventional career in the sense that she technically works on the characterization of materials. And as a consequence of her work in the laboratory, she has reimagined our theories of plate tectonics, she has reimagined our theories of dark matter, and she has reimagined our theories of what the sun is and how it works. For all three of these cases, what Anne has done is she has looked at the observational data that we have available to us, passed it through the lens of her experience in the laboratory, and come up with answers that do away with the pieces of the theory that don't make sense. So if you've ever heard of dark matter as being the explanation for the odd rotations of galaxies, Anne has an explanation that has nothing to do with mystical substances that cannot be detected. She literally looks at the galaxy and she says, well, we're misapplying Newton's laws. We're using laws that are developed for a perfectly spherical system and then scratching our heads when something that's flat and oblate doesn't obey them. And so everything that she does is centered on this idea that there are answers available to those who seek them. And it is deeply in the spirit of the program. It's a really amazing conversation because she is the first established physicist that we have spoken to who, without any drama, says that black holes don't exist, and who advocates for something that our dear friend pierre-marie Robitaille advocates for, which is that the surface of the sun is not a gaseous plasma. It is exactly as it looks. It is a liquid that is able to produce the perfect black body that we can see from Earth.
If you're interested in this kind of thing, you might want to consider blocking off June 12th to 16th this summer because we are bringing together in person for our second conference an incredible lineup of cosmologists, theorists, philosophers, communicators to look at what's going on with this black body situation. What's going on with the Big Bang? Things don't seem to be adding up like they used to, and it feels like we're on the verge of some pretty amazing paradigm shifts. So if you want to join us and come out and talk about these things and meet the scientists behind these ideas, check it out. We're meeting in Sesimbra, Portugal this summer, June 12th to 16th, and it's going to be an absolutely historic and incredible time. I would love to see you there.
It's also going to be a real party because I just realized as we were sitting down to record this that it marks the 5-year anniversary of DemystifySci. So in addition to being an absolutely epic conference, it is also going to be the place where we mark what is quite an auspicious day for us.
Is that going back, by the way, to Beyond the Podcast?
I think that's when we published our first interview with David Lindley.
Interesting. Okay. All right.
I might be off. Old. Yeah, I know. I might be off by a little bit, but it's right around then. I think we're going to it's going to be a really good time. Everybody is going to really enjoy having come out. And so I really, really encourage you, if you're interested in these topics, come meet up with us, come meet up with the scientists, and come meet up with one another, because this shouldn't be a project where everybody is just spread around the world and listening to us in isolation. You deserve to hang out with your friends that are interested in the same nerdy subjects that you're interested in.
And remember, guys, this project since the beginning has been funded entirely by our patrons. We love our patrons. We love seeing you guys every Sunday morning. We get together over Zoom, hangouts. And the reality of the situation is it's an incredible model because you can give something as little as 75 cents a week, which I think is the lowest tier, $3 a month. And ultimately, those contributions do scale up to allowing us to put more and more and more of our time towards this project to make sure that you get better and better conversations. So, take a look at your paycheck. Can you just afford the tiniest little sliver to help us keep going? It would mean all the world to us, especially in these really sketchy financial times that we're living through right now. So think about it. We would really, really appreciate your support. And you can find us at patreon.com/DemystifySci.
There's a bunch of other ways that you can get involved with our project and involved with us. One of my favorites is a new segment that we have begun that is called Paradigm Drift. We collect names all month of people that have theories of how the world works. We put them in a hat, and then those who get pulled from the hat during taping have 60 seconds to present their idea, and we interview them along with our guest panelists for about 10 minutes afterwards and help you get your ideas out into the world. We help you formulate your ideas better, and we really, really emphasize the fact that it does not matter if you have a degree, it does not matter if you have studied this thing inside of the academy for decades. All that matters is that you have an interesting idea and that you are able to explain it to the rest of the world. So the link for that is in the description. It is also up right over here. And so I hope that we see you at the next taping of Paradigm Drift on March 25th, 6:30 p.m. Pacific.
Even if you don't want to present a theory, you can hang out in the audience and be part of the Peanut Gallery. It's always really fun to chat with people that are hanging out there. So same link will get you to the Zoom for that webinar. And yeah, it's going to go down. It's going to be incredible.
In the meantime, like, comment, subscribe, tell your friends, leave a rating on a podcast store. Any little thing that you can do that spreads the word about what we're doing here at DemystifySci that helps move the needle of how people think about the world and theories and about your right to imagine the way that the world works and openly discuss it with others accomplishes exactly what we're trying to do here. And so we depend on your support. We hope that you will do so. And for now, enjoy the conversation with Dr. Ann Hofmeister about new ways of seeing the world.
The scientific revolution starts now.
The DemystifySci podcast.
Let us see in the dark.
We still don't understand light. We still don't understand gravity. Those are the big questions. They've been big questions for hundreds of 500 years, even longer, back to Euclid, back to the Greeks. So those sort of things are what I'm interested in.
I love that.
So that's actually kind of an unconventional frame, right? Because I think that people on the street might be surprised that we don't understand light or gravity. Would you agree with that?
Yeah, I think most people feel like we have equations for light and gravity, and that's good enough. I mean, the word theory in physics masquerades for an equation, whereas in something like biology, you need this kind of mechanistic explanation that's a little bit different. I think it's one of the only sciences where an equation passes as a theory, which is a really interesting situation. And so I think most people think, okay, well, there's these equations for light and gravity, so we've got it. And oftentimes pop sci or, these magazines or people on YouTube who are interpreting the equations will reify these different mathematical parameters into substances so that it sounds quasi-mechanistic at the end of the day, but it really isn't. And so I just love that you brought that up, because one of the things I always run into when I'm teaching astronomy is that unlike a biological laboratory where we can do these controlled experiments with test tubes here on Earth, all you have when you're talking about what's up there is light. And we don't really have a very good mechanistic, at least a consensus mechanistic idea of what light even is, Is it a transaction between atoms? Is it these little energy blobs that's just flung off that are kind of magical? Is it a particle? Is it a wave? Like, there's all these open questions that point to a great mystery at the center of it. And if you don't have that mapped out, then how in the world can you interpret what's coming into your telescopes?
So, can we make the case for somebody who hears that we don't understand light or gravity yet? Who's like, what do you mean we don't understand light or gravity? Like, I think that Shiloh kind of opened the door to that, but, and do you think that you can lay that out? What you mean when you say that?
Well, Shiloh is the mechanism. We don't understand the mechanism. So we argue about, is light a particle? Is light a wave? But one of the problems is we can only measure light through its interaction with matter. We cannot measure light with no interaction. So that's kind of a puzzle. And gravity, we've argued about that one too. What's the source? What's the cause? And why does it have the 1 over r squared dependence that's similar to the Coulombic forces that we associate with light? So I see a lot of things. What happened around 1900 is quantum came to be. And people based quantum on classical physics without understanding that there were flaws in classical physics. So those flaws have carried over, and that's part of what I'm working on is fixing problems in classical physics.
Okay, so let's lay out some of the problems of classical physics that you've come across then.
Thermodynamics doesn't take rigidity of solids into account.
All right.
So it's only based on gases. And this is more a math thing, but you really can't relate 4 variables. You can relate 3 variables through the differential chain rule, but you can't relate 4 without introducing something else. So Maxwell's equations for thermodynamics are an error.
I think most people wouldn't associate Maxwell with thermodynamics off the top of their heads. They think of his electrodynamics.
Yeah, no, he contributed to thermodynamics.
In what capacity? Was this a field theory of heat transfer? Or?
No, the differential equations, like ds dp equals, I'll get them messed up without looking at a piece of paper. But there's chain rules with 4 variables that go to Maxwell, and you really can only do 3 mathematically. So, and he also was the kinetic theory of gas he was involved with. So Maxwell-Boltzmann transport theory, equilibrium, Maxwell-Boltzmann speed distribution, those are all real important things that he did.
Do you think that trying to use the ideal gas laws for everything was just this hopeful naivete about universalizing something?
Yes, it was naive. It works very well for gases with small atoms, but the bigger the atoms, the more the flaw. And gases are much simpler. They're simple things.
And so I guess for me, from the outside, I look at technological progress, I look at the Industrial Revolution, I look at all of the things that have come down the pipeline, and I'm like, well, they can't have been that wrong, right? Like, we seem to have made it quite a ways. Where do you think that the wrongness really starts to become instrumental and important?
Well, I guess we can go back to thermo. Thermo's massage so everything agrees.
What do you mean? What do you mean by that? Explain.
You combine heat capacity with some other variable and you make everything agree, so the phase equilibria work out. You change the free energy functions, and you have something that's workable. But the biggest, for solids, the biggest term is their elastic energy, and that's been left out of thermo. So that's something I've been working on. Some of the things are right. It's not that everything's wrong, but there's lapses here and there, and some of the lapses the lapses affect earth science and astronomy, because those are things that we're looking at things too deep, we really can't measure directly, or too far away where light is our only probe.
So basically, the problems come down at the margins when it comes to putting together cohesive stories about these things that are too big and too far.
In certain areas, and we make the same. I also make the same mistakes over and over again. So we assume the infinitesimal exists, and it's not true. I mean, there's the classroom thing where you take a half a step, you take a step, then a half a step, then a quarter, and you should never reach the wall. Well, no, you're going to reach the wall because the infinitesimal really doesn't exist. And
it's just a very it's a convenient tool for approximating curves, essentially.
It's a convenient tool, but we can't measure things out to infinity. We don't attain infinite speeds. And the infinitesimal is one of the problems. This is long ago, and I'm trying to remember. It was a bishop, and I can't remember his last name, was arguing with Newton and some other people about the infinitesimal not existing, that this was a problem for physics. And where the problems come in then is explaining nature and reality.
Yeah, I often try to work this out every year in my lecture course too, where it is that there's clearly a metaphysical divide, because some physicists seem to understand that mathematics is used to approximate patterns in nature. And some physicists, perhaps the ones that get the most attention, seem to insist that the mathematics is the foundation from which nature emerges, and therefore these mathematical these fantastical solutions, say infinitesimals, infinities, singularities, undetermined factors that emerge in equations, that they represent sort of ruptures in physics itself, as opposed to a proper boundary condition for the extrapolation.
The bishop that Anne was talking about is Bishop Berkeley. I thought that it might have been. And he criticized the use of infinitesimals in calculus, calling them the ghosts of departed quantities, which I think is very poetic.
Where do you think that divide comes from, though, between which side do you experience more in your interactions with other physicists?
I don't interact with a lot of people. I'm a loner. So it's just partly what I was shoved into, that I was a tenured faculty at UC Davis 30 years ago, but gave that up so my then husband could get a better job without the politics. And I've never been managed to move back into the teaching position. It just wasn't going to happen.
And so as a theorist, you don't have to interact as much. You just publish your ideas and kind of
theorist and experimentalist. Actually, I'm predominantly experimentalist. So I measure heat transfer, spectroscopy, and thermal expansivity with dilatometry. So it's the heat transfer that's the basis a lot of my ideas.
Dilatometry? That's one I haven't heard of before.
Oh yeah, it's a pretty special technique. You measure the thermal expansion of basically a rod, or you hold it in the apparatus with a push rod. And then as the sample expands, it pushes on the push rod and you record that. So it's the most accurate technique, but what it doesn't do is measure atomic spacings. It records everything in the crystal. So it's closer to reality. It records the water that's absorbed in the crystal, the defects, the grain boundaries. So I have this instrument and I can't get it funded because the crystallographers oppose me tooth and nail.
On the basis of what?
Because they believe in their work and they don't want to hear that there's a different way, a better way to do things. So I just can't cut through with that. And partly, I'm getting old. I'm 70 now. So whether someone evokes this prejudice or not, I think that is a detriment to me for me to get funding.
What is the benefit of dilatometry versus crystallography? Because when I think about crystallography, I come from a biochemistry background, and so I'm thinking about people that are purifying proteins and trying to figure out their crystal structures.
The difference is the crystal structure is the ideal compound, whereas dilatometry measures the bulk material. So for some applications, you want the crystallography, like the identification, and for other applications, like modeling how the plates, Earth's tectonic plates are contracting or expanding as they heat up, you want the bulk measurement. So
Interesting. So it's basically more of a real world measurement in some ways, as opposed to
world. It's real world, more for rocks and materials than for perfect crystals.
Did you pioneer this method?
Oh no, it's been in engineering, and there's plenty of documentation that it's three orders more accurate, more sensitive for thermal expansivity than crystallography is. But no, it's just and it doesn't help that the program director is a crystallographer.
So you mentioned your work on plate tectonics. This might be a good segue to talk about that theory, because I found that to be really intriguing as well. Could you tell people a little bit about that, and maybe how this method relates to it as well?
It does, but I haven't gone that so far. So for the plate tectonics, for the last 50 years, we've assumed the whole mantle is convecting, and there's umpteen people doing models on this. The problem is, and they admit it, what's the heat source? There's not enough heat energy. The radioactivity is nothing. So the assumption is that when the planet formed, the gravitational potential was converted to heat energy, which is retained in powering it. Well, that's a problem because the gravitational potential was converted to spin. This is Kelvin's idea of gravitational potential being the way how starlight's made, and that was overturned a long, long time ago. But the idea has hung on that gravitational potential gets converted to heat, which is magically retained. And
basically, it would have cooled off by now if that was the case. I think that was the Helmholtz.
And then there's the spin. The energy of the planet's spin is immense. Stars are even larger. So the yellow type G stars like our sun, the youngest one, the fastest spinning ones, go around at about 4 to 6 hours.
Wow.
Our sun spins 30 days. Takes 30 days to go around. So that energy has been lost, but it existed, and it accounts for the gravitational potential. So that wasn't young star spin fast wasn't known by Kelvin when he formed his idea. So it comes afterward, but
I think if I might add, just for people who are interested in that, I think there's something. I think that the way that it was eventually defeated was that the sun should have burned itself out in a matter of tens of millions of years, essentially, and people were starting to discover these dinosaur bones and things like that. There was new archaeological science. Archaeology was brand new, but they were beginning to suspect. Darwin was, of course, coming up in the midst of this, and people were beginning to suspect that the Earth was really, really old, actually.
Yeah, and then radioactivity came along, and that's what did the Kelvin's mechanism for starlight in.
Yeah, and then of course that ended up failing as well too, right? Because they discovered the sun was made out of hydrogen eventually, and the gene's idea of radioactive decay powering it was no longer tenable.
Yeah, no, now we have another problem, the neutrinos. So
Interesting. All
What's
right,
the
so
problem with the neutrinos? That there aren't any?
the measurements aren't near what the reactions say they should be.
I see.
I want to come back because I want to talk about the core dynamics of the stars eventually, but I want to make sure we make it through this proposal about the plate tectonics. There's another interesting thing too, maybe you can weigh in on, which is that they haven't really found these convection cells that are necessary as the conveyor belt mechanism, right? So we always, in high school, we learn about this conveyor belt of convection that kind of moves the plates around. But it seems like when they do how do they do those studies now? They do these cool studies where they show the upwelling.
Seismic tomography.
And it doesn't really seem to correspond to any convection cells necessarily.
Well, this is the crazy thing, right? So the bottom of the ocean floors is, I think, 200 million years old. And like the idea is that there's this upwelling at the mid-ocean ridge, new crust is being formed there, and it gets pushed aside and then subducted at the continental margins. And that's basically the unit of the cell. But now as they do the seismic tomography studies, there's not actually an upwelling underneath the mid-ocean ridges.
This is actually new to me. I haven't looked at the recent articles. So,
it's just really astounding because it seems like there isn't a new place to go. It doesn't seem like there's a theory that people have on tap where they can say, okay, well, we thought that it was mantle convection, but in actuality, it's probably something else. And it seems like you're on the track of it being something else and that we don't need to have mantle convection in order to make sense of this.
What I'm arguing is that it's forces. You need to move big things, you need to have forces. And so gravity is the big force. Gravity drives landslides, rock slides, orbits of planets. So why wouldn't it be driving the motions of the lithospheric plates?
And what is the source of that gravity?
Well, there's two sources, actually. The main thing is the east-west drift, which was discovered by Wagner and others 200 years ago, maybe only 100.
I think it was about 100 years ago, yeah.
Yeah, I think it is about 100. But so the east-west drift is most of it, and the seismology group in Italy, Doglioni and others, have shown that the whole lithosphere is rotating slightly slower than the inside. So that's the east-west motions. That's his contribution. And our contribution is that the Earth is an oblate spheroid. So it has a force that's compressing it at the poles, expanding it at the equators. And since the lithosphere is brittle and it basically is underlain by a weak, partly melted layer, the low velocity zone, that lets it crack. So you have cracks that you have a crack that breaks up plates and lets them move. And this east-west continental drift that goes with the differential rotation. So that's the main part of the model. And then the perturbations I want to call on another. So that's a force. That's a gravitational force. It's the force of gravity combined with Earth's spin is changing it from a nice sphere to an oblate and creating asymmetric forces. The other thing is we tend to think of the Earth and the moon is a nice two-body system where the moon's going around the Earth. That's not the case at all. The system was known to Laplace 200 years ago. The system is the sun, Earth, and moon, where both the Earth and the moon go around the sun, but sometimes the moon's faster, sometimes the Earth's faster. So they stay together as they go around, but it's not a two-body system, and the moon doesn't move around the Earth. It moves around the sun.
And so is the last component some kind of interaction of the sun with the Earth and the moon?
Yes. So the sun's force on the moon is double that of Earth's. Double. And
just because of spacing?
Just because the sun's so big, even though it's far away, the sun's force on the moon is double. And so the other thing is the moon isn't in the same plane as the Earth. It isn't at a stable Lagrangian point. It isn't in the same plane as the barycenter. The center of mass between the Earth and the moon goes around the sun in a nice circle. But the moon and the Earth do not. They kind of bobble around this barycenter plane. And that's you can't balance the forces on the Earth. It's geocenter. You can't balance it on the moon. So there's a bunch of, there's small forces, but they're not small. I mean, they're small compared to the sun pulling the Earth and the moon around. But they're big enough to do some damage, and it's the imbalance that causes it. The other thing I'd like to call on comes from my son, Everett, who's been involved in these projects. He's a mechanical engineer. And what he said is that cyclical forces cause failure much more easily than static forces. So the fact that the Earth is spinning and being subject to these imbalanced forces is what's perturbing the plates from the basic east-west motions. It's not much, but it's real.
That's really interesting, especially, I don't know if you've ever, I'm sure that you have looked at the various databases of plate motions, where they have, I think it's just GPS sensors that are spread across the plates. And if you look even at North America, there's these crazy places where the motion is not a simple east-west motion or north-south motion. There's literally some kind of crazy gyre that's centered over the Pacific Northwest, where the plates appear to be moving in some kind of spiral direction. The Juan de Fuca plate is coming down along the coast, and so it's not some kind of neat flow of just, coming from the center of the ocean to the coast and subducting, and then the plates of the continent just kind of float on top. It's very complex. And it seems rotational. So I don't know, that makes a lot of sense. Do you think that that's the fact that Venus doesn't have a moon? Do you think that that's why it doesn't have plate tectonics?
Yeah, it doesn't have a moon, and it doesn't have any spin. So it's spin orbit coupled. So its day is as long as its year.
I think twice as long.
Twice as long. So that's one of the things we mentioned in the paper, that the plate tectonics, you have to have the body still hot, so you have to have a brittle layer over a soft layer, and you have to have a big moon and near enough to the sun that the gravity makes a difference. So those are the main things we see, and the sun's force on the moon being 2.2 times the Earth force is the sun's pulling the moon away and elongating what you'd call, it makes the reduced orbit, the orbit we can calculate an orbit around the Earth. It makes it more elongated. So the three-body problem explains that too.
I was wrong about the year. It is about the same. It's a little bit longer than the year on Venus. Just make sure that nobody freaks out in the comments section.
Keep your astronomy bona fides.
Yeah, it's a little bit Venus's spin is a little bit retrograde.
This is totally out of left field, and I don't expect you to have an answer, but have you thought about the oddities of Venus, where it doesn't, it spins very, very slowly in the opposite direction of all of the other planets? It's got a bunch of weird stuff going on. Have you thought much about it?
Well, it's spin orbital coupled, and it does have a big lump on its belly. So that helps to pull it into an orientation. There's also Mercury's nearby. Mercury's tiny, but it's still going to put a force on Venus. What's going on in Venus's interior? I don't know. It lost its spin energy, and one thing Bob and I have shown is that the spin energy is equally important to the radioactivity, even more important in the Earth. So that's a big energy source, and Venus and Mercury lost theirs probably very early on. So, I mean, that's the extent I've thought about Venus, no more than that.
That's fair. I didn't. It was kind of out of left field. What were you going to say?
Speaking of crazy ideas, can we go back to the plate tectonics for a second? Do you imagine this? Do you, I don't know a better word, but do you subscribe to the idea that the continents were all formed into one giant blob on one side of the Earth at some point, this Pangea thing?
They could have. It could have been. The problem is, it's hard to go back very far in history. So the ocean floor, the oldest parts are 400 million. That's just some real tiny spots. Like you mentioned 200 million. That's the old Pacific. But going back further than that, we use magnetics, and then what's the true polar wander versus the apparent polar wander? So people argue about this. I don't know enough to get into it. That is, I do know it. The further you go back, the more difficult it is. So they certainly were together. The Atlantic didn't exist a while ago, but what happened before then, I don't know.
I appreciate that. Yeah, anytime we talk about things billions of years in the past, you need a little bit of sugar to swallow these theories.
To be fair, I don't think Pangea was billions. I think Pangea was really billions? All right, I'll look this up.
I think so. I mean, I think a huge part of the argument has been that those continents do seem to kind of fit together like puzzle pieces, and that if you look at the stratigraphic records, there's these overlaps in different mineral mountain ranges between the different continents.
300 to 200 million years ago.
Oh, wow.
The Pangea
All right.
date.
Gosh, I'm batting
So that's
low
right,
today.
That's right. We have some information on the ocean floor. But yeah, I agree. Pangea existed, but before then, I don't know what was happening.
Well, it's really interesting. So we, as part of what we do on the show, is we collect fringe theories, and we approach it from this standpoint of truth is stranger than fiction. The realm of what is possible is far beyond the relatively narrow window of whatever we think is possible right now. Like if you go back 200 years and you told people the things that we believe now, they'd be like, no, that's insane. It's not humanly possible. And so you have to assume that there's a whole collection of things that fit that frame for right now, which is that 200 years in the future, we're going to look back on ourselves and be like, God, we were so stupid. And one of the things that we've come across is this theory of expanding Earth. Have you heard of it?
No.
Well, it sounds completely insane, but back, you mentioned Wegener at some point, and around the same time, there was another gentleman named Carey, and the two of them had very different ideas about how the continents came to be, because they're still trying to explain these overlapping stratigraphic structures and everything. And Carey's idea was that if you just make the Earth smaller and leave the plates the same size, that they'll all fit together really nicely. The main problem was for both of those gentlemen, actually, and it's worth pointing out, Wegener's ideas were not accepted in his day.
So,
but both of these gentlemen, neither one had a mechanism by which to achieve the motion of the plates. And
but Wegener's was more reasonable to people.
Yeah, I think ultimately the convection thing that we've talked about, this convection conveyor belt thing, rescued it. But I'm pretty sure he was a fringe scientist in his day. Like people were, the mainstream academic community was not happy with that guy.
He was a meteorologist.
He died on the ice. Nobody gave him a cup of soup.
Oh.
Yeah, he went to Greenland to some Arctic research station and something went wrong. I think they ran out of food. There was a storm, and he died there. But I remember when we were looking into this, I was reading about it. He was his father-in-law was really instrumental in basically telling him, abandon this tack. Like, do not pursue this. You will be forever reviled and mocked because who are you, meteorologist, to be proposing these scientific theories? And he insisted anyways, and was vindicated for the last 100 years or so. But what you were saying about Carey is that Carey at the time was saying that the Earth was smaller, and so the reason that the ocean floors are 200 to, at some small places 400 million years old is because as the Earth expanded, that was the new crust that was formed. And the argument for expansion never had an internal mechanism. So it's like, there are still people now who you go and you talk to and they're like, matter is being created on the inside of the Earth, and finally enough matter was created, and that's what caused it to rupture. And it's like, those don't totally hold together, but there's other astronomical data, right, that's coming.
Well, there's some really cool stuff in planetary science right now concerning alternative models for the formation of Earth-like planets in terms of evolution from Neptune-like planets. And so, I have no idea. Like you said, things that happened billions of years ago or millions of years ago. But there is a case to be made that, and you can do a back of the envelope calculation on this, that the compressive energy of smashing a rock at the center of a Neptune, if that atmosphere was relieved either through photoevaporation or some cataclysmic process, that there would be some elastic rebound that could potentially result in that kind of expansive process that Carey didn't have access to when he was imagining this. I'm not saying it's the case. I'm just saying that we've calculated at some point, and I think that in order to expand the Earth to the size, I think it's about 75% originally the size that it is now in terms of volume. And the energy is available if you smash it in the center of a Neptune. But that's a pretty far out idea too.
I would agree.
But crazy, the universe is full of crazy stuff. The fact that we're a bunch of atoms sitting here talking over Zoom is pretty far out. So
I was just like trying expanding Earth on people because it would be, I think that there's a lot of ideas that litter the past of science that over time get rehabilitated. Like little threads that people have left in the past that they propose and they don't necessarily follow up on, and then somebody 100 years later ends up reading their paper and they see some insight for some problem that they haven't been able to solve. And with the lack of convection currents inside the mantle, there's obviously this astronomical effect and the gravitational effect, but I also wonder if there's some. I love the idea of there being a longer history of the Earth that isn't the history that we currently see it as having.
Well, there is. We only have little pieces on the continents of very old rocks. So most of what was on the surface has been recycled. It's gone. Eroded back into the sea. Who knows?
What do you make of the certainty that surrounds ideas that are built out of so few data points?
We don't like to admit we're wrong. So scientists as a whole tend to be more positive about things than is really warranted. Scientists don't like to say, I don't know. These are also just basic human traits too. Nobody wants to be wrong.
Yeah.
Well, yeah. I mean, their whole role in society is to explain stuff, And so if they can't do it, then who can? And I think that puts a lot of pressure on individuals to come up with an answer no matter what.
I like that you've othered the scientists as the they rather than the we.
I'm in my my audience member
I see.
suit right now. All right, cool. So that's plate tectonics. What about you? You've been cultivating a community of people looking at the dark matter idea from a different lens. Maybe we can talk about that a little bit.
Okay, I guess I want to say one more thing about the plate tectonics is we've explained the observations that mantle convection has, and so I wrote this down. Our gravitational model explains the complex pattern of plate motions, which we talked about, the limitation of tectonics and volcanism to Earth's outer layers, which is with the mantle tomography you mentioned a minute ago, that you don't see the plumes. We've explained similar continental and oceanic heat flux. The oceans don't have the radioactivity continents have, but this differential rotation means there's friction. There's frictional heat generated under the oceanic plates. So that's why the fluxes are equal. And the last thing is we did talk about the uniqueness of plate tectonics to Earth. It's not on Venus. You have to have all the big size, the high spin, and the big moon near the Earth in order to have plate tectonics. So sorry, I just wanted to.
No, I think that's really, I'm glad you reiterate that.
What Carver Mead said struck me as absolutely true. We make the observations and then the theory comes afterward. So the problem with mantle convection is it doesn't explain the observations. So I like to think my model of the forces is where to change gears and look at it in different ways and go further than I have. But I don't know how to convince people.
It's also when things that don't make sense start to add up, right? So when continental drift and plate tectonics were the state of the art, we had no idea what was happening on Venus. We had no idea what was happening on any other planet. And so now as we start to develop more nuanced understandings of what's happening not on Earth, we have to place Earth in the continuum of everything that is possible. And I think that that's kind of a radical shift that's happening everywhere in science right now all at once. And so it feels like what's happening is a constriction of curiosity because of what Shiloh said, where it's like, okay, well, the role of science is to say that it can explain. And if we go through to maybe, I don't know, I like to place this after World War II. Science more or less has one set of tools for being able to to collect data about the world. And then in the aftermath of World War II, I think that there's a technological explosion when it comes to everything from telescopes to particle accelerators to microscopes to various machines that can measure these extraordinarily tiny forces, atomic microscopes. And so now there's this vast sea of things that have to be integrated into the story.
We have more data than ever.
Yeah.
Also the story, the necessity of a common story really glues the people together. And I think that earlier in our country's history or in the history of the West, religion would have taken on that glue. And as rationalism became more dominant in society, I think that the scientists had to take on a lot of that sociological burden of gluing the narrative together for a people.
And I also think that science is maybe young enough where it just hasn't gone through that many of these dramatic shifts in ability to gather information about the world. Like, I have a feeling that there are eras of method, and when the method changes and all of a sudden you can see more, it's like somebody's turned the light on in the room and now you can actually see color and you can see things that aren't right next to you. You're required to radically reformulate everything, and we don't have we have a frame for doing that kind of slowly in specific disciplines, but I don't think that there is a frame available yet for everything all at once has to change. And I know that we don't have a frame available to it because every single time we talk to somebody that has a crazy idea, they're like, I have one crazy idea. I don't have multiple crazy ideas. I'm not a total weirdo. But this is my one crazy idea. Everything else is correct. And then you talk to somebody else and they're like, well, actually, this is my one crazy idea.
Mm-hmm.
Everything else is totally correct. And you're like, oh, that's crazy, because if you integrate across all of the disciplines, everything is a crazy idea and warrants a massive shift, but no one is willing to be the person who's like, hey, all of this has to go. Except for you.
I'm trying. I'm causing trouble.
Somebody has to.
Are we satisfied with plate tectonics for now?
I think so. Let's do dark matter.
All right.
Yeah, let's talk about your experience in the alternatives to dark matter community.
I'm trying to think where this started.
Well, once you solve plate tectonics, you have to go somewhere. So
You have to go somewhere. No, it started. No, the oblate. Actually, in a way, it did start with the plate tectonics, because I wanted to explain why the heat of accretion couldn't be retained. And of course, I was getting a lot of flack. So I decided, well, if temperatures are really low, then we don't have to discuss the heating up, and we can just compare the states more easily. So I worried about accretion. That's a 212 paper. And in doing so, that led to the oblate and the galaxies and in all sorts of directions. So I actually don't remember the actual step to dark matter, but partly it's just my training in physics is reality. So how can matter exist that doesn't interact with light? And that's thermodynamics. All matter has finite temperature. So if you have matter that doesn't interact with light, it can be at 0 Kelvin, which violates one of the main laws of thermodynamics. So then we look at, well, why do they think this dark matter exists? And it goes back to measurements of galactic rotation. The tangential the stars move around the center of the galaxy, and we can measure the tangential velocities from Doppler shifts. And that was done in the 70s. Vera Rubin and some other people, and it's just boomed. There's countless measurements now.
And they're going too fast.
No, they're going just fine.
Well, everybody seemed to have believed they were going too fast.
Well, the thing is that the basic model of Rubin's time, Gallagher, Ford, I can't remember all the people, but they thought the flat galaxies should have a pattern of star velocities like the planets orbiting the sun. So the planets orbiting the sun, Mercury is faster than Venus, faster than Earth. It goes down in this nice trend. The problem is in the solar system, 99% of the mass sits in the sun. So the planets are in the sun's spherically symmetric field, and they give that simple trend. But the galaxies aren't like that at all. The galaxies, half of the mass of the galaxy is outside half of the radius that we see, not 99% at the center. So, and the other thing is the galaxies that are not orbits. The stars are not orbiting the center. It's gridlock. So if you've ever been in Boston, you can't move your car until the car ahead of you goes. Well, this is the same with the stars in the galaxy. Our sun can't move unless the star ahead of us goes. So they're coordinated. And
Is that gravitational interactions
It's
between
all
them?
gravitation. Every star interacts with every other star, and it's a pattern. So the galaxy is an object. It's not a collection of independent stars. The galaxy is one object. So actually, the thing Bob and I
Kind of like a lattice inside of a material or something.
actually, we've got a picture in one of our articles of the spiral galaxies comparing them to a hurricane. They look the same. And people fly in these planes through the hurricanes to measure the wind speeds. The pattern of the wind speeds in hurricanes is similar to the pattern of the star speeds in galaxies. They're spinning. The galaxy's gas, it's spinning. You don't have to have a solid object. So we've just developed this model based on galaxy spinning, not having orbits.
Well, in the case of the hurricane, it's the thermal process. Are you pointing to thermal processes at play in the galaxy as well, or are you just that's the analogy?
That's the analogy. It's the gas moves. The gas in a hurricane moves in a coherent spin pattern that scales up to the spiral galaxies. The hurricanes have arms.
Which is a gridlock kind of situation too,
Yeah,
I think is what you're saying.
Situation. So you can't analyze a galaxy considering independent orbits. You have to look at the whole thing.
You said something interesting that I might have misunderstood, that the matter that we can see in the galaxy is not the actual distribution of substance, where there's things that we can't see.
There's plenty. There's dust and, well, we can, what the astronomers map out in their Doppler pictures is mostly the 1 centimeter line of hydrogen, but they can also map stars, and they agree, the motions agree, or CO gas. I forget what all gases they can map, but they're recording.
Did you mean the 21 centimeter line?
Yeah, 21 centimeters. Sorry,
Okay,
21 centimeter. That's the main
neutral hydrogen.
neutral hydrogen for the Doppler shifts.
And so what's the evidence of there being other material there? Or did I misunderstand?
There's no evidence of dark matter. The problem is the analyses. I didn't explain it right. That's not you misunderstand. It's me not explaining it right. So the dark matter comes from treating the galaxy as if the stars orbit, and treating the galaxy as if the forces are in accord to Newton's spherically symmetric law. So there's nothing wrong with Newton's law. The problem is the galaxies aren't spherically symmetric. So you can't simply apply that formula. And what we did is we applied the formulas that come from McLaurin, Todd Hunter, and Gauss for the oblate. So the oblate, I have a balloon, it's a little better. So if it's something spherically symmetric, Newton's law holds in all directions. But if it's oblate, there's less mass north-south and more mass around the equator, so the forces are different. And so the forces all the way around don't all point to the center. The things off axis, and there's a different force here than there. So actually, it's symmetry breaking. So if you take it, I know you've taken physics courses. When you break symmetry, all hell goes loose. So
yeah, you end up with all sorts of bizarre intermediate axis theorems at play and all sorts of madness. I mean, I think that the key revelation here is just that when you look at the dark matter solutions that are proposed there, they are this spherical halo. Like they're trying to sphericize the galaxy. And your claim is that the galaxy is clearly not a sphere, and we can't treat it like a solar system, which you can approximate as a sphere because most of the mass is in the star.
Mm-hmm. That's right. Yeah, that's exactly right.
It's really interesting as you explain this. I'm thinking about the power, both the power and the limitations of mathematics. Because if you have something that's symmetrical and easy to work with and easy to calculate, it gives you the ability to make extraordinarily fast progress because you're not struggling with what the system actually looks like. And what you're saying is, well, no, actually, in a system that deviates from the proverbial spherical cow of physics, all of a sudden everything is much uglier and requires a more difficult calculation to arrive at reality. And so if we demand that everything follows the simple mathematics, we run into problems because the simple mathematics don't actually map neatly onto reality, which is much messier. And there's something in here about the power of math that lets you do stuff. Where I think that...
And the value of simple, like people really love elegant mathematics and the universalization of elegant mathematics. They really want there to be a simple quantitative story for everything in the universe. And unfortunately, the closer you look at anything in the universe, the more complex it becomes. You know, some people have made the argument that it's irreducibly complex, depending on how close you look.
Well, it's just crazy to me because we talk all the time about the difference between describing something mathematically and understanding it intuitively or visually. And there is a school of thought in physics and in science whose fundamental metaphysics is that reality is that which can be described by mathematics. And if you cannot describe it mathematically or you cannot treat it neatly with mathematics, then that's not what reality is. And it's almost like a math-first metaphysics, which says that like the math is the Platonic ideal of the way that nature looks. And if we look out and we see something that appears not to fit, then what we have to do is we have to introduce something like dark matter in order to rectify it with the perfection of the mathematics, because the mathematics describe the perfect reality. And so if we see something different, we must be wrong. Versus a different approach that says, hey, this math is like really ugly and very difficult, but this does appear to be what we see, and I can explain to you visually and intuitively like why it is so, but I don't have a really neat universal equation that would allow you to just wantonly use it under all conditions. And I think that there's a huge tension between these two worldviews where there's a need for a simple mathematics that can be then plugged into all sorts of other projects and disciplines and discoveries and a holistic system where if you rely on visual and more intuitive explanations, that's much harder to do. And there's not really a question in there. What were you going to say?
I mean, yeah, we're back to the metaphysical divide, right? Yeah.
It just strikes me as being so central, and I'm just starting to really figure out why it is, because I've always wondered. I'm like, why do we come up with these crazy explanations?
Well, dark matter is so much fun too. Like people just love the idea of some magical, mysterious substance. Like, we could pick on black holes too, or something. But anything that has these, mind-bending explanations that give people a sense of, what is the word? Like the re-enchantment of nature. I feel like there's this sociological thread that I pointed to earlier where religion has lost its dominance, myth has lost its dominance, and people really, really have this sense that reality is enchanted. Our personal experiences, our loves and passions point to something greater than atoms doing these mundane processes. And I think that people really want to see them in the sky, just like the ancient peoples saw their gods in the sky. We want to see the re-enchantment of nature as well.
You mentioned black holes, and I wonder, because right now, isn't the theory that there's a black hole at the center of every galaxy?
Or at least it's tiny. If one exists, and I don't think they exist, it's a tiny mass compared. It's like 10 to the 6 suns is the idea, whereas the galaxy Milky Way has 10 to the 12th suns. So that's
supposed to be like millions of other black holes in in the galaxy too. Hey, I've never actually had a physicist at a university on the show before who said they don't think that black holes exist. So, could you comment on that?
Well,
I agree, but I'm just
it's called the mystical beast of physics, and the current idea is we see some intense light at the center. Well, the problem is you don't have to have any mass at the center. That's not required. Think of a bicycle wheel. You got a hub. The wheel itself will spin around, but you don't have to have anything at the center. So the sphere is not the only possible star shape. The oblate spheroid is not the only possible star shape. You could have a torus, a donut. So I kind of like that idea that it's not a black hole, but we have a donut of star matter at the center that's producing this light and spinning around like mad. But whether I'll investigate that in my remaining years is another question.
I mean, it definitely smells a lot like dark matter or something where you see anomalous motions, oftentimes something orbiting nothing, and you stick a placeholder in there, right?
Mhm.
And dark matter kind of feels like that. Black holes kind of feel like that. And honestly, every time I start seeing this black or dark word in astronomy or astrophysics, I think like, okay, well, this is a placeholder. Like we just haven't figured out what's going on in these particular situations yet,
Mm-hmm.
which is fine. I mean, I think that's kind of how science works in some sense. You know, I always think back to the phlogiston caloric, you know, where you have incredible fluid flow equations that describe how heat is transferred. And it just turns out that that motion of the molecules transfers in a way that appears very congruent with fluid flow. It doesn't mean it's an actual fluid, but it does look like one if you don't have this concept of motion transfer at the sub-unit granularity.
We always kick phlogiston. Like everybody always kicks phlogiston because it was supposed to be the substance that was responsible for combustion, and it was this fluid that moved through matter. And obviously, it was terribly wrong. It was actually oxygen, and Lavoisier proves it. But I'm like, I think that was a step in the right direction. Like, it's not humors, it's not demons, it's not, the power of God or some like vital force. At the very least, people are trying to move in the right direction. And so I think that that's kind of, as you look through the past history, the thing that really sticks out is that people obsess over the fact that phlogiston is the final answer, as opposed to being a stepping stone for something that a generation from now will be radically different. And I think that dark matter is the same. Like people are pointing out, dark matter comes as a direct consequence of saying, hey, Newtonian dynamics don't work here. And people now go out and based off of whatever's the style of the day, the same way that phlogiston was, come up with an explanation for how to account for those non-Newtonian dynamics. And at least as long as people had some humility about the fact that the first answer probably will not be the right one, I think that it's kind of a stepping stone in the right direction. I think what's alarming is how universally beloved it is as a magical feature of the universe that leads people to black holes and to multiverses and to wormholes and white holes and like all of these other things that just seem...
They're so much fun.
I was going to say seem juvenile, but I think that's my Soviet nature coming through.
But I mean, it's not, I guess I should give some other people credit. It's not just me and Bob who've argued that there's no dark matter from the rotation curves. There's two other groups, Sipples and Pavlovich, who happen to be bankers and financial experts, came up with a matrix method to calculate the mass of the stars from the velocities. So their solution describes the equatorial plane. Our solution describes the oblate. And then Fang and Gallo model a thin disk, which is, well, it's this cross section, but thin. So their answer is a little larger than ours. And it's the same thing, that they take the velocities, all three groups take the velocities and extract the mass. And the masses are, I forget, within a factor of 1.25 of each other. So it's these different, it's just a different shape. It's not Newton's law being wrong. It's misapplying Newton's spherical form of his law to an object that isn't a sphere.
Pardon the interruption, but I have to ask you for a favor. If you enjoy the podcast, if you have listened to a few episodes and you really like the things that we do here, please come over to patreon.com/DemystifySci. For 75 cents a week, which is not very much at all, you can help us keep this ship going in perpetuity so we never have to slap advertisements or sponsorships on this thing, and we remain forever a product of the relationship that we have with you, the listener.
I just want to say I'm loving talking to you. This is fantastic. I wish I had found you 20 years ago. I
wasn't doing good stuff 20 years ago.
I climbed as high as I could in the academic tower looking for someone who would have more down-to-earth explanations for a lot of these fantastical things. And yeah, it's hard to come by. That led us to really starting this podcast in the first place. But yes, I just want to say I really appreciate you coming by and sharing this perspective.
Well, I thank you too, both of you, Anastasia and Shiloh, for this opportunity. Because I'm research only, I don't get much opportunity to talk about my work. And I've managed to alienate lots and lots of people.
Well, it's interesting. I've been playing with this idea of science podcasts like what we're doing, where we bring on different theorists we do 2 of these a week. And it's not always science. We do economics and archaeology and all sorts of stuff. But I've been playing with it as a kind of extension of what was really popular before the career-driven peer review system that's very popular now. Because back in the 18th, 19th centuries, there was this Royal Society of Letter Correspondences, which was a very different matter than the publishing system we have today, where people were floating ideas, sometimes half-baked ideas, and they're really just talking to one another as independent investigators trying to make sense of reality. And so I wonder, I hope in its best form that the podcast space serves as a means to keep those conversations going in a place that they don't quite fit into the, really into the peer review system that encapsulates most of the scientific dialogue today.
Or the consensus
Even 50
system.
years ago, you'd see a lot of articles with a question answer at the end. The conference proceedings were all like that. And no, we don't do that anymore.
Yeah, something changed really radically when people began doing science as their primary career. I know there was some of that in the 19th century, but for the most part, a lot of the titans, we were talking about electromagnetism and light, like a lot of these guys, Thomas Young was a physician, these guys had other jobs oftentimes, right? It wasn't that they considered science necessarily a professional avenue, but it's a pretty big industry now because, of course, it's been merged with technology, production, statecrafting, all these other things. So I think
people have just forgotten that it's possible. Like it's been a generation since it was on the forefront, and whatever has happened in the interim has erased it from people's memories, and we're here to reawaken that. I think that's probably fair to say.
Oh, our fancy instruments are expensive. That's
yeah, it's true.
There's that
That's
as
true.
well.
Have you seen the maintenance contract on one of those? I mean, it's not like the instrument itself is the basic cost, right? It's like you got to have a guy who comes once, twice, 3 times a year that tunes the whole thing up and makes sure that it runs. It's not free.
So, we were originally just planning to talk to you about this dark matter and the plate tectonics, but one of our listeners in our Discord server sent me this paper a little, very recently that you published with You've been referring to him as Bob, I think, Robert Chris.
Yeah, Bob Chris, yeah.
And it's a really interesting paper for a couple of reasons. But
Well,
maybe we can.
thank you.
There's a couple of really interesting pieces here. The thesis itself that star interiors might have a different thermal profile than the one that we're used to. This extraordinary ultra high, like 10, what is it, like 10 to the 7th Kelvin temperatures. That there might be a different story behind that. And along the way, there's some really fascinating details. Maybe we can get to them later. But could you lay out that idea for us?
Well, actually, this goes back to what we were talking earlier about thermodynamics. Thermodynamics does not include heat transfer, even though Fourier's theory came earlier. Fourier, by the way, was in the foreign service for the French government. He wasn't a career scientist. So that was left out of thermo. And Stefan Boltzmann's law, which is another important connection of flux and temperature, was left out of thermodynamics. So basically what we've done is it's really Stefan Boltzmann's law that governs the insides of stars, and stars are spherical. Our sun is really, really close, and it's a good approximation for most stars. Galaxies are like pancakes, but stars are pretty close to nice round balls. So all we really did was combine Stefan Boltzmann's law with the spherical symmetry and how flux depends on the radius, and the temperatures just drop off.
Yeah, can we talk about how that mistake was made? Does this go back to Eddington in the 20s?
The high temperatures?
Yeah.
The high temperatures, it's not, well, it's sort of Eddington. It's actually Emden, whose book, actually it's on my shelf over there, Gas Clouds. He modeled the quiet sun, and he called it the quiet sun, and his boundary condition was the surface of the sun was at 0 K. So it doesn't emit light.
Yeah. Okay.
And basically what's in his model is he developed the polytrope model, which is really neat. But he has to have the 0 Kelvin boundary condition, and he also assumed that the Kelvin's hypothesis, that all the heat of contracting the gas ball to a star became heat inside the star. And with the 0 K boundary condition, it was forever retained. And that's the source of the 10 million degree temperatures at deep inside the sun. That's where that comes from. And then the subsequent models take that as the initial condition. So they've got the Kelvin mistake as their basis. And then they do some conduction and radiation and convection calculations to try and evolve that temperature, see how that temperature changes with time. But it's not right.
Oh, that was another interesting part of the paper too, was that you were saying that this idea of the solar radiation changing across time in this really dramatic way is not evidenced by the geologic record.
We've had a 3-phase Earth, water, gas, and ice for as long as we can tell. And the isotope record's pretty good, even through some glaciations. Shows that it shows the Earth's cooling down, not by much, but it's cooling down. So,
and that's the opposite of what is produced.
That's the opposite. They have
in the standard theory
warming up.
That's really interesting. I mean, that seems like a thermodynamic, like a elementary thermodynamic mistake to assume that objects would heat as opposed to cool.
That's what I would argue. I think what's really solid about the paper is Stefan Boltzmann's law, and that connects flux to temperature, And we know the flux from a sphere. It depends on the radius very simply. And then go ahead.
Yeah, it does depend. It depends on a few things that are kind of interesting. There's also, I noticed that the emissivity term is dropped from your representation of the Stefan Boltzmann laws as well. So it seems like there's material properties that could play into it as well.
You don't need it. If it's a black body,
If it's an ideal black body and it's
the sun's spectrum, the 6,000 K spectrum, it's not quite a black body, but it's pretty reasonable. It's pretty reasonable. And we can only see into the sun about 600 kilometers. Below that, the sun is opaque. So on that basis, the sun is a black body.
it definitely has that thermal spectrum for sure. The question, I guess, just becomes if there are convection contributions to the heats, convection contributions to dissipation of the heats, then is it possible that the temperature that you get from the black body is representative only of the residual temperature after you've accounted for processes like convection?
Well, I actually don't think convection exists, and it hasn't been. I do know it hasn't been modeled correctly. So one of the hallmarks of convection cells is that you have boundary layers. So you got the churning middle, and then the temperature gradients are. The churning middle has a very slow temperature gradient. All the actions at the boundaries. Their solution doesn't have that. What they do is they have the temperature at the center from Emden. They got the temperature of the surface, and then they integrate inwards and make them smoothly match. That's wrong. That's a basically wrong approach. So I don't. And the other thing is that if you can only have convection if the material cannot carry the heat by conduction or radiation. And what our solution shows is that there's no problem carrying the heat. It's a simple linear dependence of thermal conductivity on temperature. That's weak.
So conduction is the big player.
Or radiation, conduction, radiation. Actually, they're the same. Conduction is radiation of infrared light, and that's actually my discovery. But it's published, but trying to get the community to look at that one is like pulling teeth.
Interesting. So you think even between solid bodies that are in contact, there's radiative transfer occurring?
Yeah, it's infrared, and it's very slow. And it's one atom will emit an infrared photon, and another atom will absorb it and then re-emit it. That's diffusion. That's what Fourier modeled. So,
what do you make of the structure on the surface of the sun, where it has the
kernels?
Granules.
Yeah, the granules that look. I mean, obviously this is analogy, but if you were to take, I've seen these demonstrations where people will heat petri dishes with some kind of substance in them and show that the convection, the Rayleigh-Bernard convection produces forms that look very, very similar to what's on the surface of the sun.
No, you're right. The granules are convection cells, but they're about 600 kilometers across, and like your petri dish, it's about the same thickness. That's what these Rayleigh-Bernard they're equant. So that 600 kilometer layer is where the lights, what we see into. It's where the light's generated. It's where the convection is occurring, and it's fluid. It's that layer should be fluid.
That's something I really want to talk about. 1 second, I want to make sure that we understand this. So when you said that you didn't believe there was convection, you were talking about these giant, what are they called? There's a convective region that's supposed to be most of the body of the sun.
Yeah,
from what I understand.
Yeah, it's supposed to be most half, a third, 2/3. It's something like that. No, that's what I don't. don't see as possible. But the convection at the surface makes perfect sense because the sun's shedding its heat out to space. There's a huge thermal gradient from the 6,000 degree surface of the sun to where we measure its light. That's a huge gradient.
Really quickly, what was the 0K boundary condition? I missed the connection here.
No, Emden assumed the surface of the sun was at 0 Kelvin.
The surface of the sun, or like just above the surface of the sun?
Well, the infinitesimal surface.
Okay, I think, but that is patently absurd, right?
But that's what he had to assume so he could combine the temperature and the gravity. He used the hydrostatic equation with this boundary condition to get at the temperature. So that's his polytrope. And Emden comes in. Emden promoted the polytrope. I mean, he cites Eddington promoted the polytrope, but it really was Emden's invention.
Is the polytrope a piece of mathematics?
It's a mathematics, and it's combining the hydrostatic equation with temperature. And I'm sorry, but I can't remember offhand what exactly the combination was.
That's all right. I want to pause for a second and really emphasize how unconventional it is to say that there is a liquid layer to the sun. Like, we've talked to solar physicists and everyone's like, this is obviously an apparent surface. It's gaseous plasma. It's not a liquid. And so can we kind of...
Yeah, it's often treated as an optical illusion. That was the second piece of this paper that really struck me, was that I haven't heard an academic scientist advocate for a true surface of the sun before. I thought that was really interesting.
Well, surfaces are phase changes.
That's right.
The atmosphere is gaseous, the inside solid from compression. It's got to have a real surface.
Certainly looks like one.
It certainly does.
Are you familiar? Have you heard of the work of pierre-marie Robitaille?
Say the name again.
Pierre-marie Robitaille.
Oh, Robitaille, yeah. No,
So he's one of the people that we've run across who's, I would say he's would you say former academic, extra academic, but he's devoted himself quite intensely for probably the last, 20 years or so to formulating a liquid model of the sun. Have you read his work at all?
I've not read. I've read his earlier work, but not the liquid model of the sun.
I think that you guys would really get along.
I'll have to look at Robitaille. I don't know how. No, it's quite. Yeah.
Yeah, we can send you some of his papers.
Well, I can look it up.
Yeah, he's got a really cool paper called 40 Proofs. What is it called? I don't have it open right now.
I can look it up.
But he has a cool paper that lays out 40 lines of evidence for a liquid nature. I mean, one of the things he points out that's just really, simple to demonstrate even to a 15-year-old or something is that we don't really have the ability to generate that beautiful black body spectrum from gases in laboratories on Earth. There's... Right? And so that, once you see that, you just take a prism out and start playing with this in your own house. It becomes a really compelling argument that there's something more tending towards liquid solid occurring. And if you go back into the literature, like I was saying, I just love these Royal Society correspondences, but people are debating this heavily back in the 1800s, back to Herschel, 1700s. And actually, this gentleman named Herbert Spencer advocates a very similar model to the one that's appearing in this paper that you advance, which is funny because Herbert Spencer, most people don't know much about him because he was a terrible social Darwinist, a eugenicist, And so he got kind of driven out of the history books, from what I can tell. But he essentially advocates for something very similar, which is a liquid shell on top of this gaseous star. And I just think it's really funny, again, how things kind of go in these cycles where these ideas, they get left behind. How long have you thought about the suns or stars that way, as having a liquid-like surface?
When I saw the granules, when I saw the pictures of the granules, it's just like you said in the petri dish. They're obviously little Bernoulli convection cells, although they're not too little.
They're huge. Yeah, I mean, and you see these flares erupt and these splashes come down, the transverse ripples on the surface. It's very shocking. The only thing that I can reason with, I've actually had astrophysicists get really, really upset with me when I start talking about this. It seems to be a real trigger point, and so I'm really excited to be sitting across from another physicist who's willing to at least talk about it. The only thing I can think of as to why people are so defensive about this is because of the ideal gas laws that they need for the equations of state for the sun.
You don't need it, but we don't know what the equation of state of hydrogen is at very high temperature and pressure. I use the ideal gas law. That's what Emden used. He used the ideal gas law combined with the hydrostatic equation and the 0 Kelvin boundary condition to get his temperatures. That's what he did for the polytropes. So Bob and I use the ideal gas law because we don't have
in the interior.
We don't have anything better. The diamond anvil cells won't reach the high enough pressure and temperatures. I've never trusted shock experiments, and they don't get that high. They're transient. They're not steady state, and they don't get that high a temperature. So all we have for equation of state of the sun, the hydrogen, is theory. And we'll go back to what Carver-Mead said, that the theory follows after the observations. So we have some problems. We have our limitations.
That is a fair point. I mean, one line of evidence that's, well, this is perhaps rooted in theory as well, is that people are now beginning to consider the giant planets like Jupiter as having some point at which the hydrogen reaches this liquid metallic form. And then, of course, the surface pressure at the sun is not sufficient for that, but there's been some evidence, at least, again, theoretically, that liquid metallic hydrogen could be metastable at some time scale from which it could perhaps be created at a lower depth than the sun and rise to the surface somehow and give us that nice platform for a black body fingerprint. But again, it's that of course, until we're able to actually demonstrate some sort of liquid substance at these pressures and temperatures, it's going to be very hard for anyone to really stand behind, I think.
I mean, the average density of the sun should be telling. It's about that of water.
Good point.
That should tell us something. And these giant stars, they have atmospheric densities, 100th, I think, for the big ones, supposedly. I just talked to Bob. He's here today too. Before I came down, and he said one thing I should point out is that in astronomy we measure these immense distances, and those they might not be exact, but we know the distances you see are immense. And so that gives credence in astronomy to these immense temperatures and other immense things which may not be real. We don't have checks. We have checks on the immense distances, the Cepheid variables, and you probably know more than I do.
Well, yeah, I mean, if the distances are incorrect, then the absolute luminosities will be incorrect as well. And there's another place, since we're talking about Stefan Boltzmann, and I pointed to this emissivity term that's often not used in the simplified version of the equations, but a lot of this is predicated on Kirchhoff's law, which stated that the thermal spectrum would be independent of the walls of the cavity which was used. But we kind of know this isn't the case, right?
Mhm.
The actual material quality of the surface really does change its apparent luminosity. And if you really start to consider that emissivity term in the Stefan-Boltzmann relationship, you
Mhm.
could also run into a situation where these distant stars have some material property of the lattice that's giving us this black body spectrum, which is, let's say, not 100% efficient. So if that emissivity drops down, then also the total luminosity drops down without having to bring the radius into things. In other words, the stars don't necessarily have to be ultra compact, or there's other explanations for getting that luminosity in line with the position of the star.
Actually, I think the problem is emissivity doesn't belong in the Stefan-Boltzmann law. So you mentioned we can't measure gas black bodies in the lab. That's true. We can only measure solids. And one of the problem is that a solid reflects at its surface. If you have a solid and light goes in, it reflects. But if you have a hot interior of the solid and you have the heat, which is also light coming out, it'll also reflect at that surface. So there was a theory developed from 1946 to 70s, and it's been confirmed that you have to be careful with Kirchhoff's law. That only applies to gases where the emissivity comes in. With solids, you actually have a reflection at the surface. So the way the experimenters dealt with it in the 1900s and beyond, the classic Lummer and Pringsheim experiment, they heat up a metal wire and they coat it with graphite. So what the graphite does, it eliminates that reflection.
Right.
So that's why.
But that's the same as perfect emissivity, essentially. Like reflectivity and emissivity are essentially inverse quantities.
So that's why, yeah. Well, they're related. They're spectral properties. So that's why Stefan and the subsequent frequency experiments have black body relationships, because they use the graphite coating. But
That's right.
Emissivity doesn't belong in Stefan-Boltzmann's law. If you
use a different material than a graphite, you would end up with a different temperature readout.
have a reflection, and we've got another paper in review talking about the solar spectrum and where reflection is affecting, how reflection affects what you see. So we'll see if that one makes it through.
Well, yeah, it also seems like metallicity could play into that, right? Because metals have that really normal reflection. They have a lowered emission in the normal.
So is the sun a liquid metal then? Is the surface a liquid metal? Maybe. I don't know. I don't know.
It could explain a lot. I don't know either. I think it's a really interesting idea, at least. I mean, it's interesting because it affects so many things downstream of astrophysics, right? So many different explanations, all the way to the black hole, as far as I can tell. Because if it's a liquid metal, liquids are essentially incompressible by definition, so you don't really end up with these star fates that are collapsing space-time or anything like that. Those require an ideal gas in order to produce them.
And there's also, the cosmic microwave background radiation that enters into the chat very suddenly, right? Because if we accept that a black body can only be produced by a solid, and then you have the most perfect black body that's ever measured, all of a sudden you have to start asking the question of, well, how exactly is that being produced?
I think a gas can produce a black body, just not in the lab. We can't do it. But these stars are big enough. So to have a black body, it has to be all diffusion or radiation. And the diffusion occurs when the light can't the light diffuses between 2 points. So it doesn't jump across the points. So I'm not technical. The sun's optically thick. We can't see light coming from the inside, just from this little boundary layer. And for the cosmic microwave background radiation, the universe is so big that you're going to see diffusion even though it's transparent at other wavelengths. So I think we are seeing the temperature of the universe in the cosmic background radiation, which is an Eddington. That's Eddington's calculation. The three he got 3K, whereas the modern measurements show 3.7K. And then the astronomers and the astrophysicists are worried about what's the anisotropy in the cosmic background radiation.
Yeah, we actually just did a podcast with a historian of physics who was walking us through all of the different predictions along the way.
Oh.
And it's funny because most of the people who made those accurate predictions were not advocates of an expanding universe or a Big Bang model. That actually persuaded people slowly along the way. Gamow famously made a prediction of like 50K prior to the discovery of the CMB, and he was one of the biggest advocates of the Big Bang model. So that was a really fascinating piece in the history of science right there.
Yeah, I mean, I think that whether or not gases can produce black bodies seems to be, at this point, like a theoretical, mathematical, like statistical mechanics explanation, right? Where it's the fact that the light, for example, for the production of the sun's black body, from what I understand, it's that the photons that are produced inside the sun bounce around for millions of years until they emerge at the surface to produce this perfect black body. And it seems a little bit like it is looking at the data and attempting to fit this gaseous model to it, as opposed to starting from a different set of first principles, where it is in fact a liquid or a liquid metal which produces the black body. And it's like, if you could produce a stable black body from a gas in the laboratory, then I think you would be able to at least have experimental evidence that could argue one way or another. But I wonder if in the absence of that experimental evidence, it doesn't make more sense to refactor our understanding of black body radiation to say that for the light to take on that incredibly specific shape, that it requires the lattice and cannot be produced by a gas.
Requires what?
A lattice.
No, I don't think so. I think gases, the problem is they have to be optically thick at the frequencies where the black body's produced. And I think that's met in the cosmic background radiation, but it's not met in the visible in the universe. So the universe it only acts as a black body with those wavelengths. The other counter evidence I would think of is that, and I haven't checked this out, but the temperatures of the big O and B stars are supposedly based on their their spectrum being shifted enough that they're 50,000 degree temperatures. But I have not looked through the data to see what the spectra look like. I did find white dwarf spectra, and they think they're 200. They think they're really hot too, 200,000 degrees, and their spectra goes way into the UV. But it's not like a black body; it's much more square shaped.
Interesting.
So I don't think it's just a matter of path length that solids are really dense, so we can measure the black body radiation in the lab, and liquids too. We can measure that from liquids, but the gases, we just can't get a long enough path length that the light doesn't go through it. So that's a theoretical argument rather than experimental. So
It's like the diamond anvil. We're waiting on that. We're waiting on that experimental proof.
They're too small. So some of the things, I think the best science is explaining the observations in a simple and sensible way. That's my belief. But sometimes you can't do all the experiments that are required. So you have to make certain leaps. And I'm trying to remember who said this, but some of the laws we hold near and dear, like the laws of thermodynamics, they were actually established on very little data. The second law, the equivalence of heat and work, there was very little data. And that was a fight. I don't know if you know the history of that one. It was Joule, Helmholtz, and Myers. And Joule begged an editor of a newspaper to publish his work on the equivalence.
I had no
I can't
idea.
remember. One of them, Helmholtz, had a brochure printed because he couldn't get it published. And I can't remember what Meyer managed to do to get his published. And it wasn't a decade afterward that it was accepted. But
it's so funny just how time and time again the textbooks paint this very nice linear story. Even the Kuhnian idea of just these revolutions just sort of happening when somebody gets a good idea all of a sudden. They just obscure so much drama that's happening below the surface, and the heartbreak of being one of these people with a cool idea that you just can't get anybody to listen to.
Like Wagner. Yeah, like Wagner. No, the plate tectonics revolution succeeded because a lot of people were involved. It wasn't just one person or two or three people, a small research group. That made a big difference. And there were big winners and big losers with the plate tectonics revolution.
Ultimately, it is in some ways a zero-sum game. The guy who advocates for phlogiston ends up being wrong. And yes, there might have been something useful in all of that work, but the final conclusion ends up being in need of radical reimagination. And so I think that that's kind of what makes all of these things so difficult. And
I love what she says, though, about it being a team sport in some sense, right? I see people who have really cool ideas that have a hard time working with other people and have a hard time entertaining additions or addendums or modifications of their original ideas. And I'm not saying they should buy everybody's modifications. I'm just saying they have a hard time even hearing people out because it seems like it's such a loner activity. So many of us scientists are just out on islands working by ourselves, and it's a bit tragic because I think it really does take a society to accept and to really move forward with these big shifts as they happen under our feet.
And so I was going to ask you to wrap us down, if you had any advice for young scientists, young theorists that are going out into the world and they're searching for things to explain or phenomena that warrant further investigation. Like, you seem like you have been uniquely able to find things that can be explained more elegantly than what is currently out there.
Well,
so do you have a lens that you use that you could transmit to someone?
It's my 40 years experience in the lab.
Yeah. So do you think that having that laboratory experience is really important?
Essential.
What about it?
It's reality. You have, it's effort. It's not effortless. It takes a lot of effort. And again, I'll go back to Carver Mead. He said it so well, that theory is based on observation. So while I don't make any of the astronomy observations, I have at least some experience in evaluating numbers and looking at these things. What do I trust? What makes sense? Before the 1900s, the experimental physicist was who was revered. But around the time of quantum, it changed to the theoretician. And now it's mostly computer modeling, which isn't theory. So I guess if I have advice, I would say do something in the lab and don't do the computer modeling. But that's for science. That's not a career. That's not going to help their careers. I mean, if I say what helps their careers, it will be very sarcastic. So, but you have to get along with people, and I don't. I've been alienated. I've been alienated, and so, and I don't think like a normal human being. So maybe that's the recipe: is just not being normal to have a real discovery, but you suffer because of it. Wagner suffered. Gauss and some of the other very special people in history were recluses. Gauss would never go to a meeting. I mean, and Newton was a known weirdo.
Yeah, I love that. I think that that's a very deep insight. One of the reasons that I really love Pierre-Marie's work is that he cut his teeth as head of the radiology department at The Ohio State University.
Yes, he did. It's
And so,
spectra.
yeah, and so it's the perfect marriage of this, a certain amount of disagreeability and also a vast quantity of experience with reality that allows you to derive some...
Especially thermal imaging of reality.
Sure, but it's like the place where the rubber meets the road is being able to see what is and then make some kind of larger frame that another story can be fit into. And so to see you approach these questions from a different path and to arrive at similar conclusions just really, really hammers home that it is a difficult path and one that requires a level of dedication that I think many people are, I don't want to say they're afraid of, but it's very hard because you do have to be disagreeable and you have to say things where people shout you down and they tell you that you don't know the answers and you're sitting there.
You might not get your Nobel Prize anytime soon.
You won't.
And there's such a legacy of the disagreeable
God,
scientist.
I wish I had this. I was reading a little excerpt from, I think it was the London Times in Thomas Young's day, and there's a newspaper reporter just talking about how big of an imbecile he was to think that a mere physician could challenge Newton about the nature of light. And of course, Thomas Young's one of the most brilliant people that ever lived, as far as I'm concerned. And so it's just wild to see that this same fear of stepping outside of the lanes was present all the way back in the early days and was being applied to people who really revolutionized the way that we understand nature.
No, this is human nature. We're talking about human nature.
Indeed.
So it goes. We must all wrestle with our human natures.
Absolutely.
But listen, Anne, we've kept you for a long time, and I really appreciate you giving us this opportunity to talk about these subjects.
Thank you. I really appreciate it. You
Fantastic.
Give me some food for thought.
Awesome. Yeah, I highly recommend you check out the 40 Proofs paper. I would just love to hear what you think in general anyways. And if folks want to check out your work, I assume that the literature is probably the best place to do that.
Yeah.
I'm assuming you're not hanging out on Twitter or anything like that.
No, most of my stuff is open access. The recent stuff is almost all open access.
Excellent. Well, with that, we will say goodbye. And again, thank you so much for coming by.
Well,
I hope folks will check out your work. And this is how it's done.
Thank you so much.
All right. Thanks, Anastasia. Thanks, Shiloh.
All right. Take care, Anne. Bye,
Bye,
everybody.
everybody.